Welcome to another part of the ISM course in Statistics 1. This time with a unit on covariance and correlation coefficients. The Pearson correlation coefficient, so to speak. And if we want to motivate this, we could start with the idea of covariance. And as the name already tells us, this is similar to what we know from variance. When we calculated the variance, this was basically the difference from the mean to the power of 2. Here we have two variables, so we are not squaring one of the differences from the mean, but what we are actually going to do, and this is the formula here, we take the difference from the first mean, multiply this with the difference from the second mean. So it's basically the variance, but split up for two different variables. So for the mathematical definition, but how can we actually imagine this? How would this actually work like? Why are we using this formula? Which actually, if you want to shorten this, would look like this. Imagine you have a lot of different points. This is basically different observations. They have an x coordinate, they have a y coordinate. So it could be different people where x is height and y is weight. Also makes sense because they're relatively good related to each other. Okay, what are we going to do in the next step? We divide this graph into 4 different quadrants. How are we going to do this? We just insert the mean for x and the mean for y here. So those are the two means. And if we put them into our graph, we see we have 4 quadrants. 1 in the upper left, 2 in the upper right, and 3 and 4 in the lower part. Well, obviously there's a positive relation in this case between x and y, so a positive relation between height and weight. And in this case, whenever we have a positive relation, most of our points are in quadrant 2 and 3. Now imagine there would be a negative relation. So the line would go from the upper left to the lower right. So most of our points in this case would be in quadrant 1 and 4. With this in mind, let's turn back to our formula. What do we know about quadrant 3? Quadrant 3, we are below our mean for x and we are below our mean for y. So all our x and y's are smaller than the mean. If we would take a look at the formula, how this would look like if I insert an x which is smaller than the mean and a y which is smaller than the mean, I would get a negative value for the first brackets and a negative value for the second brackets. Smaller than the mean for x gives a negative value, smaller than the mean for y gives a negative value. So I have negative value times negative value, which would give us a positive sign. Now take a look for the points in quadrant 2. In quadrant 2, I'm larger than the x average, than the mean for x, and I'm larger than the mean for y. So in this case, I would insert an x which is larger than the mean. So the first parenthesis would lead to a positive value. And the second one, I have a y which is larger than its mean, would also be positive. So if positive times positive would also turn out positive. So if most of my values are in quadrant 2 or 3, I would add up a lot of positive values in my formula for the covariance. So if most of my values are in quadrant 2 or 3, my covariance would be positive. Now we could play through the same thing with quadrants 1 and 4. 1 and 4, one of my values is below its one of the two means, and the other one is above the mean. Meaning, one part I have a positive sign and in the other a negative. and positive times negative always results in negative. So if most of my values are in 1 and 4, my covariance will become negative. Well, and if we just summarize those insights, this means whenever our covariance is positive, we have most of our values in 2 and 3, so we have a positive relation. On the other hand, if our covariance is negative, most of our values are in 1 and 4, and we have a negative relationship. If our covariance is 0, then approximately the same number of values are in 1, 2, 3, and 4. That's the basic idea behind the covariance. The downside to the covariance is, while it can take positive or negative values, there's no lower limit, no lower bound, and no upper bound. So it can take any value between -infinity and +infinity. And that's relatively bad, because, well, if I get a covariance of 18, question is this actually a strong relationship? Yeah, it's positive, but is this strong? How about 200? How about 5,000? How about 2.1? So it's relatively hard to compare this if we could have any value. And that's why we take a look at the correlation coefficient. The correlation coefficient starts with the covariance, but provides a version where we actually have bounds which help us to put this into some kind of context. And that's what we do on the next slide. Here's positive, positive, negative, negative, so I just told you. And if we go to the correlation coefficient, this looks like this. Well, if we recall the last slide, the part above the fraction line, that's actually our covariance. So what we're going to do is just divide the covariance by the standard deviation of x and the standard deviation of y. That's the two formulas we have here. And if we do this, we get as a result the correlation coefficient, which has the nice characteristic that it only takes values between -1 and +1. So whenever the covariance has been 0, the correlation coefficient also is 0, because whatever is above the fraction line, if this is 0, the result will be 0. So if there's no covariance, no relationship via covariance, the correlation coefficient is also 0. Additionally, what we can see, if they're perfectly aligned, we would get 1. If they're positively perfectly aligned. If they're perfectly negatively aligned, we would get -1. So we can summarize this. 1, all observations are on a straight line with a positive slope. It's -1, all observations are on a straight line with a negative slope. And 0, there's no relationship between the two variables. In particular, here I said no linear relationship. The correlation coefficient and the covariance, they measure linear relationships. So it could be that there's like an exponential relationship, a quadratic relationship. There could be any different types of relationships, and still the correlation coefficient could be very small. So always keep in mind, even if you do not find any correlation by using these formulas, there could still be some kind of relationship, which however is non-linear. Well, this then concludes what I wanted to tell you in regards to the covariance and the correlation coefficient. I hope you learned something from this and you enjoyed listening. And more of this type of sessions you can find in the corresponding playlist or the corresponding course. I say goodbye and see you next time.